This is Chapter 6, Formation of the Solar System. Our goals for learning will be what does the solar system look like? And in Section 2, the nebular theory of solar system formation. In Section 3, explaining the major features of the solar system. And in Section 4, finding the age of the solar system. So in this first section, the question is, what does the solar system look like? Instead of concentrating on the bits and pieces of small information that other people may have asked you to look at, we're going to look at the major features, the major differences, major similarities within our solar system. So what does the solar system look like? Well, the diagram on pages 138 and 139 show the overall characteristics pretty well. There's basically four major sections on these two pages that you need to look at. First of all, on the left-hand side of the double page is noting something about the orderly motion of the planets. All of the planets revolve or orbit the sun in a counterclockwise direction as seen from above the north geographic pole of the Earth. And most of those planets rotate in the same direction, counterclockwise. The second part of this two-page summary talks about the major categories of planets, the terrestrial planets versus the Jovian planets. It's easy to separate the two because Earth being a terrestrial planet, you're looking for other planets which have a solid surface, as opposed to the Jovian planets, which are mainly gaseous and, of course, have ring systems around them. And the last part of this double page has to do with the smaller bits and pieces of our solar system. Asteroids, meteors, comets, those parts of the solar system that for whatever reason didn't come together into a planet or any part of a star, but instead remained floating around in orbit around the sun. So those are the major features we're going to be looking at. There are definitely clear patterns of composition and motion, and it's much more than we're going to be looking at much more than the trivia that many people have otherwise looked at. So what does the solar system look like? Well, we know there are 4 planets making up what we call the terrestrial planets, and then outside of that there are these planets we call Jovian planets, or inner and outer planets would be another way to describe them. But notice that, again, we emphasize that the motion of these planets around the sun are all counterclockwise. The planets fall into 2 major categories, as we've just talked about, terrestrial and Jovian. There is a definite difference in the composition of the planets. There's also a definite difference in the size of the planets, as you can see from this diagram. Terrestrial planets are much, much smaller than Jovian planets. In addition, there are these things called asteroids and comets that make up part of our solar system. They are found in different places in orbit around our sun, but nonetheless they're part of our solar system. We occasionally see comets as they approach the sun if they're in a closed orbit, and of course once in a while we have a close approach with an asteroid. Possibly in our long ago geologic past we had other approaches or even impacts with asteroids. But there are some notable exceptions. For example, Uranus has a tilt which is extremely high compared to the other planets. It looks like it's almost rotating on its side. Another exception is the fact that our moon is considerably larger in proportion to the planet that it revolves around. So the Earth-Moon system is rather unusual compared to the other planets that have moons. The planets are very tiny compared to the distances between them. This series of diagrams here in the top left shows what the planets look like relatively speaking in terms of size. And then toward the bottom of this slide, you see the relative distances of the planets compared to a scene in Washington, D.C., going from the National Air and Space Museum all the way out beyond the Art and Industries building. But I'll just look at the black dots, and you see that the terrestrial planets are pretty closely packed, whereas the Jovian planets are much farther spread apart. So let's look at some of the parts of the solar system. This is, of course, the Sun. The inset that you see is the Earth shown for size comparison. Very, very small compared to the Sun. And these two pictures, A and B, show the Sun in two different forms of radiation. There's a visible light photograph where we actually see sunspots. And in letter B, we see a picture taken in ultraviolet by the SOHO spacecraft, where we can actually see these large eruptions of hot gas emanating from the surface of the Sun. So, for obvious reasons, the majority of the mass of our solar system is the mass of the Sun, over 99% of it. The Sun is made mostly of hydrogen and helium gas in a very hot or plasma-like state. And it's kind of interesting to read that the Sun is converting 4 million tons of mass, 4 million tons of hydrogen mostly, into energy each second. That's according to Einstein's E = mc squared. Here's a couple of different pictures of Mercury. Again, terrestrial planet having a solid surface made mostly of metal and rock. We assume it has a large iron core. It's heavily cratered. It has some very long, steep cliffs. And because it has no atmosphere, it's very hot in the daytime and very, very cold at night. Here's Venus, almost the same size as Earth, but the surface is of course hidden by a very heavy cloud layer. And because those clouds are above the surface of Venus and so thick, they tend to capture more of the heat that the Sun is giving off, and it ends up giving Venus surface temperatures as high as 470 degrees Celsius or roughly 900 degrees Fahrenheit. And here's Earth, an oasis of life. Water is found in all three forms: ice, liquid, and vapor. And like we said before, it has a very large moon compared to the size of the planet. There are obviously continents, there are oceans, and what we would consider life. Mars is about half the size of Earth. It looks Earth-like, but the concentration of oxygen is much, much lower, so you'd have to bring your own supply. There are volcanoes, there's a huge canyon, there are polar ice caps, and lots of Earth-like features, very similar to what we might see here. There are canyons where water flowed in the distant past, so the question is, could there have been life on Mars at one time? Jupiter is much farther out from the Sun than the inner planets. Now we're looking at one of the first Jovian planets, much, much larger and much farther out, but made mostly of hydrogen and helium, no solid surface. In spite of that, its size makes it 300 times more massive than Earth. And of course, it's one of the first Jovian planets we look at that has many moons. And until recently, we didn't know it, but we do now, it has a ring system. Jupiter's moons can be as interesting as the planets themselves, especially the 4 Galilean moons. The 4 moons are Io, which is shown in the foreground here in the picture, which has active volcanoes. Europa, which may have an ocean underneath the surface. Ganymede, which is the largest moon in our solar system, and Callisto, which we think is a big ball of ice. So these moons could be places where we would like to go visit. Saturn is also very large, not quite as large as Jupiter, but it has the ring system that everybody recognizes. It has almost as many moons as Jupiter, including the inset there you see is the moon called Titan. If it has this haze to it, then it apparently has an atmosphere. If it has an atmosphere, maybe it's able to trap some of the sun's radiation. Who knows? Maybe the temperatures near the surface could be comfortable for some form of life. The spacecraft called Cassini is has been able to study much of the atmosphere of Saturn. And then the rings themselves. Saturn being the planet with the most obvious. Two spacecraft approached Saturn very long time ago and found that the rings were not solid. They were made of small chunks of ice and rock, and they each orbit the planet like a tiny moon. So we're looking at millions upon millions of moons, very, very small moons, orbiting Saturn. But they also keep in line with each other more or less to form the ring. So the ring system itself is pretty interesting. This is kind of a diagram of the path that Cassini took in order to reach one of the moons. And as you can see, it wasn't a direct route. It had to use several planets to do a flyby to gain enough speed to actually reach Cassini, or to actually reach Saturn and its moons. So it's not a direct course. It's very almost circular, but finally reaching enough speed that it could escape the Earth's gravitational pull and, of course, fly fast enough to Saturn. So as it says here, it was launched in 1997. It arrived in 2004. That was a 7-year journey. Then there's Uranus, smaller than Jupiter and Saturn, but obviously much larger than Earth. Again, hydrogen, helium compounds make up the gases. Some water, some methane, some ammonia. But it has this extreme tilt to it, as you can just barely see by the ring system. The rings are basically around the equator of Uranus, so this planet is tipped way over. But it does have a ring system, similar to Jupiter and Saturn. And then there's Neptune, similar to Uranus, but it doesn't have the extreme tilt. And again, it has many, many moons. So we see this pattern of Jupiter, Saturn, Uranus, and Neptune, all having ring systems, all being very, very large, having hydrogen, helium composition for the most part, and they just have those common characteristics. And then there's Pluto, which has been recently thrown out of the planet club, and now we think of it as a planetoid or a planetesimal. You pick what name you want to give it, but not a planet anymore. It does have moons or objects orbiting it, much, much smaller, but until recently we thought it had an icy comet-like composition. And Charon, which is one of its moons, was very close to the size of Pluto. So if it was part of our solar system, it would have the largest size comparison between planet and moon. So what have we learned? Well, planets are tiny compared to the distances between them. Each world has its own character, but there are many patterns that we can come up with. Terrestrial planets have many similarities. Jovian planets have many similarities. So we kind of divide up the solar system into those two groups. Page 150 of the textbook has a very good summary of all the features that up to now we've looked at about the planets in our solar system. So it's a good data table to just kind of glance over to see what sorts of patterns exist. All right, let's look at section 6.2, the nebular theory of solar system formation. And the goals here are what features of our solar system provide clues to how it formed, and what is the nebular theory. We're going to look at this in a very superficial way, not getting into a lot of detail, but just understanding the basic parts of the nebular theory. So, at least up to now, this is how we believe our solar system formed. So what are the features of our solar system? Well, as you can see from the picture there, we've got lots of things happening in terms of the planets themselves being part of our solar system, and that solar system eventually coming from what must have been a very large cloud of gas and dust. All large bodies in this solar system orbit in the same direction and pretty much in the same plane. They most also rotate in the same direction. So we basically have a rule of motion here in our solar system, that from that blob of gas, there was a counterclockwise motion, not only of orbiting bodies, but also rotating bodies. And that makes sense. There are two planet types, as we've discussed already, looking at the terrestrial and the Jovian planets. Terrestrial planets are rocky, relatively small, close to the sun. The Jovian planets are bigger, gaseous, and farther from the sun. And then we have these other objects, these smaller bodies. We have asteroids and comets existing in certain places in and around our solar system. We have asteroids, which are typically in the asteroid belt between Mars and Jupiter. We have this Kuiper belt, which is outside the orbit of Pluto, basically, where some comets come from. And then we also have something way out to 50,000 astronomical units called the Oort cloud, which is exactly that, like a spherical shaped cloud around our sun, where other comets exist. But we know there are exceptions to these general rules. Uranus has the extreme tilt to its rotation, and as we've talked about before, the Earth-Moon system in proportion is much, much larger than any other planet-moon system. So what is the nebular theory? Well, we'll look at that as we go through this section of the chapter. It's basically a way of explaining how our solar system formed. And, of course, there's no direct proof of it, but based on what we've seen in other places in space, we kind of put together the jigsaw puzzle and say, this is what we think happened. So according to the nebular theory, our solar system formed from a giant cloud of gas, interstellar gas. Nebula means cloud. Of course, the cloud itself isn't hot, and it's just kind of floating around in space. But there's one thing that's going to bring it together, and that's, of course, gravity. So here's the origin of the nebula. The elements that form the planets were made in stars, and then that was recycled through interstellar space. So we have stars born in clouds of gas and dust, as you see in the top of the diagram. And then as we go clockwise around, the stars are going to produce heavier elements from lighter ones. And of course, when the star explodes, that throws the material out into space to be recycled. So it's a constant recycling of matter, of mass, that we see, or we think we see in other parts of the universe. And we think this is how our solar system formed. So what's the evidence from gas clouds? Well, we can see stars forming in other interstellar gas clouds, lending support to the theory that a nebula was responsible for forming solar systems. So what have we learned? Well, motions of large bodies like our solar system, they're all in the same direction, basically in the same plane. There's two major planet types. There are swarms of smaller bodies called asteroids and comets. There are, of course, exceptions like Uranus, the Moon, and others. And finally, the nebular theory holds that our solar system formed from a cloud of interstellar gas. As you can see on page 155, that's a good summary at the top there. That's a good summary of how it all seemed to happen with the large interstellar gas cloud, the cloud coming together under gravitational pull, heating, condensing, bits and pieces colliding. As the gas cloud gets smaller and smaller, conservation of angular momentum makes the spinning go faster. It forms a flattened disk. And of course, as these particles get even closer together, temperature rises. And ultimately, at the center of all of this, we get nuclear fusion. And that would be the sun. Nuclear fusion is what the sun is powered by now. So there's a pretty good description of it there.